Welcome to EPG Pathshala. We are looking at a series of courses in computer networks. In today's module, we will be looking at the implementation details of a router. So, what goes inside a router is what we are trying to look at today. So, basically we will look at the architecture of a router and try to understand exactly where this processing of the IP layer that we have been talking about actually takes place. So, we know that there are two functions of a router, namely routing and forwarding. So, routing is about running these algorithms that we have talked about, the routing algorithms, intra-domain and inter-domain routing algorithms, RIP, OSPF, BGP and so on. And second function that we have to do is forwarding. So, forwarding is forwarding a datagram when it comes from some input link to an output link. So, both these functions have to take place together in the router, and we need to look at what are the various components that are there in the router which facilitate both these functions to take place. So, if you look at the overview of a router architecture typically, what it would have is a set of input ports. Remember, we have been so far talking about input ports and output ports in routers. So, there will be input ports and a set of output ports, and there is a high speed switching fabric which is connecting the inputs with the outputs, and there is a routing processor which is responsible for setting up the switching fabric, right, which takes care of how packets are switched from one input port to another to an output port. Okay. So, if you look at this, you can look at the functions as being split into two different planes. One is the control plane and the other is the forwarding or the data plane. So, the routing, management, all these things come under the control plane and typically are handled by software, and this fast switching that takes place is what is called as the forwarding or the data plane, the forwarding data plane, that is normally done in hardware. So, this is normally what the a router architecture would look like. What exactly goes into each of these input ports, what goes into these output ports, and how this high speed switching fabric is designed, those are the things that characterize what a router normally does and how it functions and what its performance is. Okay. So, if you look at this, the forwarding tables are computed normally by this routing processor under the control of the routing protocol, and that information is pushed to the input ports, so that the forwarding tables can be set up. So, the forwarding tables are set up at the input ports, and this information is used by the input ports. When the packet comes in, it looks at the forwarding table and based on that sends it to a corresponding output port, right. So, this is basically what happens. We have looked at the routing algorithms, we also looked at what forwarding means. So, now we are trying to just put these two together. Okay. Right. So, let us look at this input port functions. What exactly are the functions that we have at the input port? So, if you look at the input port, you have you can split up whatever is happening into three different layers. There is a line termination which is basically a physical layer function, okay, which is responsible for bit level reception. So, basically receive it as signals or whatever and look at the bits that are received. Next is the data link layer function, which is the link layer protocol, which is responsible for, since we are at the input process, is responsible for the receive function. So, for example, this could correspond to your Ethernet receive function that you have here. Okay, this will be the second function at the input port, and the third part is the third layer, that is the IP or the network layer related function. So, you have lookup, forwarding, queuing are the various things that take place over here. Okay, and from here the packet will be sent to the switch fabric. And the switch fabric, remember, is the one that is used to interconnect the input ports and the output ports. So, at the input ports, basically we are looking at the three layers functions, the physical layer, data link layer and the network layer functions, and of course, we are more worried about what is happening at this network layer function, where lookup and forwarding and queuing normally take place. Okay. Right. So, given a datagram destination, what will happen here is that the output port will be looked up from the forwarding table and it will be sent to that particular output port. So, it is basically a match plus action kind of a function that will be specified here. What is it that needs to match, and if something matches, what is the action to be taken. So, that is the information that will be specified here, and that is what will be used to do this forwarding function. Okay. So, the goal obviously is to complete this input port processing at line speed, because what we mean by line speed is the speed at which your line is working and the rate at which packets are coming, and we would like to process it at the rates at which the packets are coming in. So, the goal over here basically is to complete your input port processing at line speed. So, if you have a 10 gigabit per second line or a 1 gigabit per second line that is coming in, we would like to finish this processing at that same speed. Okay, that is the main goal at the input port. Okay. If the datagrams arrive faster than the forwarding rate, then what we will have to do is we will have to queue them. So, which is why you have a queuing function over here. Ideally, as the packets come in, if you are working at the link rate, then you will be able to directly do the lookup and forward it immediately. But if this process is taking a little more time, then it will get queued. Okay. So, one of our goals obviously will be to reduce the amount of queuing that is done, or move or do the queuing in such a manner that does not cause any performance bottleneck, right. So, that is what we have to be looking at. So, that is about the input port. Next we look at the switching fabrics. Now, switching fabrics are the ones that are used to transfer packets from the input buffer to the appropriate output buffer. And the switching rate, that is the rate at which the packets can be transferred from the input to output. So, the switching rate normally is determined by the type of switching fabric that we have. So, it is often measured in terms of multiple of input output line rate, as a multiple of input / output line rate, and if there are n inputs, then the switching rate should be n times the line rate. That would be the desirable rate. Now, why do we say that? Because we have n inputs. Obviously, we want all of them to be switched simultaneously without any blocking. So, in which case, if your switch is able to work at n times the line rate, then it will be able to process them without any delays. Okay. So, these are the general requirements of the switching fabric. Now, commonly they are used switching fabrics are of three types. Okay. One is a memory based switching fabric, another is a bus based switching fabric, another is a crossbar kind of a technique. Now, if you look at these are more or less they kind of talk about the evolution that has taken place with respect to how these switches are actually designed. The earlier systems were memory based, later they were bus based, and now mostly you have crossbar or other hardware switches that are used for constructing these switching fabrics. Okay. So, let us look at each of these one by one. So, if you look at switching via memory, as I said, these are more or less first generation routers. So, they are basically traditional computers with switching under the direct control of a CPU. So, you will have packets being switched from the input port, they would come to memory. So, the memory acts as your switching fabric as such, right. So, everything will come to the memory, and from memory your processor will move it from the memory to the output port, right. So, and then it gets sent out to the output port. So, this is basically what will happen, and here you can see that the speed will be limited by the memory bandwidth that you have, because you need to have 2 bus crossings per datagrams. That is, for every datagram that comes in, as we saw, it has to come through the bus from the input port to the memory, and then from the memory to the output port. So, there are 2 times that every packet will have to be sent through the bus. So, you have contention for the bus, then you have to worry about how much of memory capacity is there. So, those are all the issues that we have to deal with when we look at switching via memory. So, as I said, it is a first generation router. So, it has been replaced by much more sophisticated systems. So, in between we had what is called as a bus, switching via bus, which is a bus acting as the interconnection network. So, here what is done is that the datagram from an input port memory is shifted to an output port memory via shared bus. So, that is, you do not have a centralized memory, instead you have memory which is part of your input ports and memory which is part of your output ports, and datagrams are switched from the input port to the output port, but they go through a shared bus. So, here obviously there is a lot of bus contention that would take place, because the amount of switching that can take place will be limited by the bandwidth of the bus. So, if you have a very high bandwidth bus, that will facilitate faster switch, but if your bandwidth of the bus is lower, then the rate at which the switching gets done will be slow. When you had these earlier Cisco 5600 kind of series of routers, they were able to work with about 32 Gbps bus, which was sufficient at that time for access and enterprise routers, and now of course we go for faster interconnection networks. So, next is switching via interconnection networks, typically a crossbar kind of a network. So, the idea here is that we want to overcome the bus bandwidth limitations. So, we have various interconnection networks like Banyan networks, crossbar and so on. In fact, many of these interconnection networks were initially developed to connect processors in a multiprocessor system. So, many of these have been adopted and adapted for the switches in the other routers, and they kind of provide dedicated or fast connections between inputs and outputs, and they are also normally programmable. So, you will have some kind of, they are called as programmable interconnection networks or programmable switches. So, you can program these switches to provide the required input port to output port switching. Okay. So, we have very advanced designs in terms of these kind of networks. So, you have fragmenting of datagram into fixed length cells and switch, and the cells are the ones that are switched through the fabric. So, if you look at ATM networks, ATM switches and so on, ATM switches typically will have many of the are basically interconnection network based switches, where the packets which are coming in themselves are normally cells, they are all of fixed size, and so the switching can be done very fast in those kind of switches. So, what is done here also is that sometimes in order to facilitate fast switching, your packets may be fragmented and then the switching could be done. Okay. So, Cisco 12,000 series which is about 60 gigabit per second, they use the interconnection network and so on. So, next component that we have is the output port. So, we looked at the input port, then we looked at the interconnection network and then the output port. Now, the output port, if you look at, again you will see that there are 3 layers of processing that take place here. One is what happens at the network layer, and then at the data link layer, and then at the physical layer. So, from the switch fabric, data comes in to a buffer, right. So, normally it is buffered here before it can be sent out at the rate at which your line is working. So, you have a datagram buffer and queuing process, and so basically some queuing will happen here. So, there are some queues and buffers present here, and from here it will go to the link layer protocol to do the send function. Basically, your Ethernet send function will take place here, and then it goes to the physical layer from where it is sent out. So, the important functions that take place are here. Basically, what happens here are 2 things, buffering and scheduling. So, buffering is required when datagrams arrive from the fabric at a rate which is faster than the transmission rate. Okay. And scheduling discipline is the one that is used to choose among queued datagrams for transmission. So, it may not be a single queue that you have here, but you could have multiple queues for data coming in from different input ports. Now, why would we want to do that? We may want to provide different quality of service for data coming in from different users or from different input ports. So, you would have identified those flows, and for certain flows you may want to provide higher priority, or you may want to provide faster processing, in which case you put the different packets that are coming in from different input queues or from the different input ports into different queues here, and you process from these queues and send them out. So, to select from one of these queues, a packet from one of these queues also requires some kind of a scheduling discipline. So, there are various scheduling disciplines that are used, common ones being things like first in first out, and then or you could have something like a fair queuing, and then you have something called weighted fair queuing. There are various techniques that are used. We will look at these scheduling disciplines later when we talk about quality of service and how these disciplines are helpful in supporting different quality of service. So, right now remember that there is a scheduling discipline that will kick in at this layer in this particular module, which will take care of picking up the packets from the queues and sending them out on this data link layer and then out through the physical layer. Okay. So, this is basically what happens at the output ports. Now, at this layer what we also need to remember is that since datagrams are queued, are buffered, it is possible that it could be lost due to congestion. So, what is congestion? When you have more number of packets coming in than what can be handled in the queues over here, you will have to end up dropping packets. So, you will, because of the lack of buffers, could end up in packets being dropped and therefore lost. Okay. And since we have a scheduling discipline here, we can have priority scheduling, or we can have differential services that are provided. So, who gets best performance? These are, and what about network neutrality? Okay. These are a kind of issues that can be handled at this scheduling discipline. So, these are 2 important things that people normally play around with in order to make sure that you are able to take care of congestion and also take care of differential treatment being given for different packets. So, now normally what we are worried about here is what should be the size of the buffer, so that you can avoid congestion. So, those are the things that people study a lot in terms of what is the rate at which packets are coming in and how much of buffer is required and so on in order to avoid congestion. Okay. So, let us look at this output queuing a little bit more in detail. Okay. So, typically what happens is, say let us say at time t, let us assume that the packet red colored packets have to be sent out to this port. So, you at time t, say packets move from the input to output port, right, buffering when arrival rate via the switch exceeds the output line speed. So, what happens here is, now the packets are coming in from here, right. So, if the output speed is less than the rate at which packets are coming in, now there are 2 packets coming in here. So, what happens at one, if you look at what happens 1 packet time later, you will find that there are 2 packets which are queued over here. Now, the other packet which is meant to go to this could probably be switched. Similarly, another packet which is meant to go to this could also be switched, but the packet that is meant for this output line here, the one on top, you can see that there are 2 packets which are identified as red in color, 2 packets coming in, they are not able to be sent out, therefore, they will be queued over here. Okay. So, this is basically what happens in terms of output port queuing. Okay. And as I said earlier, now if this fills up, obviously you are going to be losing packets and there will be delays because of the queuing, and eventually there will be losses because of this queuing. So, we talked about the buffer size being important. So, how much buffering should normally be done? What should be the size of my buffer? So, as I said, this is normally determined based on characteristics of the network, and the typical characteristic that we look at is the RTT, the round trip time. Okay. So, normally the average buffering is set as a rule of thumb is said to be equal to a typical RTT, let us say approximately 250 milliseconds multiplied by the link capacity C, whatever is the link capacity. If I have a link of capacity 10 gigabit per second, so and if I assume that I have a 250 millisecond RTT, so you will require about a 2.5 gigabit buffer in order to be able to support fast processing. So, essentially you can say it is determined by what we call as the delay bandwidth product, right. So, what is the delay multiplied by the bandwidth, that will give you the capacity of the buffer that should be used. Okay. Of course, there are recent recommendations with where when you have n flows, you have a thumb of again a kind of guideline which says that the buffering should be equal to RTT into C divided by square root of n, that is when there are n flows that are to be considered. Okay. So, in fact, a lot of research gets done in this area in terms of what should be the size of the buffers, given that you have different rates at which traffic comes in, and since that kind of varies with time and varies with the kind of applications that are running, there is a lot of scope for designing and for identifying these kind of parameters and designing very good fast switches and routers. Another option that we have when we talk about this kind of buffering is, so here we talked about a buffer that is maintained for each output. Another option that we have is what is called as the shared output buffer. So, in this case there is a common or a large memory that is there which is shared by all the output links. So, one of the advantages here is that you will have better utilization of memory, and the packets will be distributed across memory, and only the pointers to the packet locations must be stored in the queues, because in the queues you do not really need to store the data. The queue only basically maintains pointers to the locations where the packets are stored. So, packets are basically in memory, and again of course, there are other issues here which is with respect to how effectively you will be able to access this memory, and you will be able, again memory access speeds could also become a bottleneck in this case, but this is another option that is also considered. Okay. Now, we also said that there may be a requirement for queuing at the input ports. Now, when would I require queuing at the input port? That typically happens when your switch fabric is slower than the rate at which packets are coming in, right. So, the fabric being slower than input ports combined will cause queuing to occur at the input ports, right. So, in this case you could have queuing delay and loss due to input buffer overflow, okay, not due to the output buffer overflow, but due to input buffer overflow. That is one possibility, but one of the reasons why input port queuing is normally not recommended is that you have a problem called the head of line blocking. Now, I will give you an example of this head of line blocking. If you look at this case now, so I have a red packet which is supposed to go here, and a brown packet is supposed to go here, and a green packet is supposed to go here, let us say. Okay. So, now what happens is that now these 2 packets have to go to this particular output port here, this red packet from the first one on the input side and the last one on the input side. So, now if this packet goes, it has to be is being transferred to the switch. So, obviously what happens is that the lower one cannot be transferred, so that is blocked. So, now while this is blocked, what happens is that the green packet which is just behind that can actually be switched, because the port to the green port is actually free, right. But what happens is that since the red packet here is not got out yet, it was the red from here which got out, right. So, that has already got into the output buffer there, and now it is this this brown packet also got shifted here, right. These two things took place in this in a time instant t, let us say. So, at the next time instant, when the next packet is to be scheduled, you find that there is place for this fellow to go out, but this fellow is not able to go out yet, okay, and you find the green one, even though this can actually be switched, is not sent out because it is somebody is sitting in front of it, blocking it from being transferred, right. So, we call it as head of line blocking. There is another packet at the head of the line which is blocking a packet which can actually be transferred, right. Because of this contention, this one which actually does not have a contention is blocked. Okay, this is normally a problem that occurs when you have input port queuing. So, and again this is also one of the reasons why input port queuing is normally not preferred, but in certain cases where it is absolutely necessary, it will be used. So, you can see that given all these considerations, the switch fabric, the design of the switch fabric is very, very important. So, if you have a very fast switch fabric, you can make do with no buffering at the inputs and have the buffers only at the output queues, and with that you will be able to achieve fast data transfers. So, to summarize, what we have looked at in this module are basically the internals of the router. So, we have looked at the input queues, we have looked at how the interconnect is important and the output queuing. So, when we talked about the input queues, we talked about problems like the head of line blocking that could take place, and we talked also about the importance of the interconnects. Now, in fact, you will see that there is a lot of design that takes place at the interconnect level. So, the speed at which the interconnects work is a very, very important aspect, and then the output queues, the buffering, the scheduling and the various things that take place at the output queues become another important aspect. We will actually spend a little more time on these issues when we look at the quality of service parameters and how quality of service is provided at the routers. So, you will be looking at that later when we look at various parameters with respect to the quality of service, and you will see that further issues like scheduling, traffic shaping, traffic policing and various other functions also come into play in order to provide the quality of service. So, you will actually see that the way the routers are designed and the way the switches are designed is a very, very important factor when you look at the entire network layer design as such. So, so one needs to be always aware of what actually goes into these routers. So, we will end with that. Thank you.